Hi, my name is Roland, and on my channel I have released several videos about the topic of earthing and bonding while using off-grid inverters. And today's video is somehow a missing link for the understanding between the American system and the rest of the world system, more or less, because on my channel, as probably on every others, the majority of my viewers are coming from the United States. But because I'm actually from a country where Northern American electrical system is not used, I still try to kind of find a common ground, so keep this somehow interesting for everybody on this planet, more or less. So as I said, most of my viewers are coming from Northern America, and also most of the commenters are from those countries. And in those comments I can then always kind of see that there is still confusion, and in today's video we will try to clarify some things and find a common ground, because it's all about how to make electrical systems safe. And yeah, this is a universal problematic. It's not just European, American, Asian or whatever. So yeah, so please stay with me, and we will take a closer look in the Northern American system, in the rest of the world system, if you want to call it like that, and how to actually really make our DIY off-grid systems. This is what we are actually talking here about, those safe, as it would be a grid installation. Okay, so let's look into the matter. So a viewer of my channel recommended to me I should take a look into a video from Mike Holt, who is an expert in writing the National Electricity Code of the United States. And so as I was looking, grounding the basics, more or less video, I think we are all talking about the same thing, but there is some sort of problem with the terminology of what is called what in the United States National Code, and what is then of course a little bit different in the 230 volts world outside of Northern America. So initially I want to just make it very clear we are speaking terminology and definition, so that everybody is on the same page. When it comes to National Electricity Code, then it of course, this is talking about a grid connection. And what we are talking about is inverter grounding and bonding in an off-grid situation, or if you might use a hybrid inverter, but this is also talking, when it's about grounding there, it's also how to do it when the inverter is in the off-grid mode. When I say the term bonding, what do I mean? Well, bonding is always if you take two parts of a system, so in this case it is the grounding circuit, and connect this together, marry it with the active neutral circuit. What is the equivalent of this to a grid? This would be the part inside a transformer which is connecting the center tap of the wiring of the secondary coil to the grounding side, to the housing of the transformer. So our bonding wire is doing nothing else than connecting. Northern America is talking about system grounding side in a housing installation to active neutral, right? So our bonding wire connecting PE or system grounding to the neutral to the active neutral. So now I already said a term, system grounding. What does system grounding in the National Electric Code mean? System grounding is whenever a fault between the hot wire and the grounding circuitry, so everything what is connected, every metallic object, the metallic shell around the appliance which is connected to the grounding system, if there is a fault there, then the current is taken over this system grounding circuit, and it will cause enough current so that the overcurrent protection device inside of that circuit will trip. So the circuit will be powerless and the safe situation is then given. And this comes from our bonding wire, which is connecting the grounding side with the active neutral. There we have closed the loop so that current which goes over the grounding system can flow back to the inverter, and the loop is closed. So what does it mean when I'm talking about inverter grounding? So inverter grounding, when I say this is the second part. This is the equivalent of the transformer in the grid having its ground rod, and the neutral point which we just created, the ground neutral point, is wired, connected to the grounding rod, and so we have tapped into the earth. And what this gives us, the opportunity, of course, that a ground loop is created. And why do we need that ground loop? We have two advantages there. One is we can prevent an overvoltage event happening, and the second is we have the chance to install ground fault detection devices. So in every modern installation we are using RCDs, or in United States GFCIs, and they only work if you have a ground loop available. The second part has to do with the protection of humans when humans by accident come into contact with the hot wire and current flows over the human, over the ground, back to the earthing rod of the transformer, or in our case of the inverter. We have to avoid one mistake, that people sometimes think that the inverter, if they install it, is like similar to an appliance, but this is not true. The inverter is the beginning and the end of our circuit. The power is generated there, and the power will return, or must return, to the inverter to close the loop. It should never be mistaken as an electrical appliance. This is a power source, and this you have to see like this, right? Sometimes people install an inverter somewhere in the middle of the circuit behind RCDs or stuff like that, and then they wonder why there's a problem with tripping RCDs or not correctly functioning protective devices, because they mistake it as an appliance. But an inverter is the power source. It is similar to a grid transformer, it is similar to an emergency generator or whatever. The power source is a power source, and everything after follows. Okay, so these are the definitions. So we are speaking about creating our TN point if we want. If we don't want it, we can keep it as a IT, but we will now speak about the details why you should maybe use or not use a certain configuration in your system. Let's look at the world map of different electrical systems. We have two different systems globally. One is the Northern American system, which is USA, Canada, Mexico, and some Middle American countries here. And there's also a spot here in Japan. And that system is actually the so-called split phase system, and the main difference to the other parts of the world is a relatively low line to neutral voltage. So you can see here some countries 100 volts, but in average USA, Canada 120 volts. They have a higher frequency as well as the rest of the world, but the frequency in our case is not as important to mention. And then we have the other parts of the world, and those have either 220, 230, 240 volts. So in average it's a 230 volts line to neutral voltage. So about double the voltage as the Northern American system. So what this actually means when it comes to protective systems, we will then see in a moment when we are talking about protective earthing, and also when it comes to protective devices like using of RCDs, GFCIs, etc. Let's come to the first maybe common confusion, and that is about code, so electrical code. I have here the code of Austrian installations. Then of course every region, every country, they have something similar to this, and the code is always about how to make an electrical installation as safe and as conform to the regulations so that you can connect it to the utility grid. So code has primarily something to do with the utility grid regulations. Now we are actually talking about off-grid installations or inverter installations. This is a more and more upcoming issue in the future. People are getting solar systems, they're putting solar panels on the roof, then they install an inverter, and then they connect their whole house to it or just parts of it or whatever. And this is where you actually have to look into, maybe also into some points of the code only. It's not necessary to follow all these installation requirements. But what is of course interesting, if somebody is installing an off-grid system, which in some countries might never be checked by anybody, right? So nobody will come in to your door and check if you have installed an off-grid inverter code conformal, because you are off-grid. And being off-grid and doing your own electricity supply means that you took over the part of your electrical utility. So you are now responsible to make your installation safe or not. You can of course skip many of these points which are written inside a booklet like this, and it will be okay. It's fair enough not to follow the code word by word if you don't want to. But there is one chapter in a booklet like this, and this is about safety measures, and I would say the recommendation is follow at least the safety regulation, because this is about your life and the life of your family, of course. A lot about safety regulation inside code like this, electrical code, is about earthing. The reason why it's about earthing is because a grid connection always comes in a form which is including a bonded earth. There's 5 different earthing systems globally defined, and 4 of those are bonded to earth. And that means that you have to follow certain procedures to safely connect your home installation, or whatever, industrial installation, whatever there might be, but there are procedures to safely connect this to the grid. Because in case of faults in your installation, something will go on there. There will be currents flowing back to the point of source, which is a transformer. And if you do not follow those procedures, you would actually cause an unsafe condition, and in the worst case, you could be electrocuted. So that is why code is talking a lot also about these safety measures, and that of course is very individual if you have a grid connection to your property, and it can be not just regionally, it can also be locally very different. But when you do now an installation by yourself using an inverter, in the first moment you're actually free to do anything you want. You can choose each of the 5 defined earthing systems and implement that into your installation. But as you will see in a moment, there is advantages and disadvantages to each of these systems, and let's talk about that now. Okay, here I have a table. You can find this in Wikipedia about earthing systems if you want, and it is showing us the 5 defined earthing systems we are working with. So when it comes to a grid connection, we have spoken about code. Then you will typically only have to do with 2 different systems here, maybe a third one, but the most common are the TT system and the TNCS. In some places you might still come and find a TNS system. But when it comes to grid connections, you will very rarely find IT and TNC. We have been talking a lot in our case study about IT system, right? Not to use any earthing. So now, when it comes to your own installation doing with an inverter, you are actually initially free to choose whatever you want out of this. You are not bound to any sort of code or grid conformal installation, especially when you are totally off-grid, if you do not have a bypass to the grid. So how do you know which one of these you have to choose? Well, to initially make a choice, I would suggest to take a look into the safety column here. And of course, what your plan is, what sort of installation you actually want to do. If you just want to connect a single appliance or just have an inverter charging up your phones, whatever, running your laptop, so not much behind it, then you can of course go for an IT system. It is very simple to set up, not much to think about. But if it comes to installing a property on it, a house, a workshop, a cabin, and you have a lot of appliances on there, then you should really look into choosing the correct system for you. And if you look into the column here, safety, then you will see TT, safe, IT, less safe, TNS, the safest, TNC, the least safe, TNCS, safe, right? Let's see why the IT system is less safe. What is the safety risk there? So the safety risk there, I mentioned it in previous videos, is when it comes to more than one fault. So a double fault, or here also over voltage, is a safety risk in IT systems. We can take a closer look into that here. So here we have the explanation why is the IT system not safe. So in IT systems, a single insulation fault is unlikely to cause dangerous currents to flow through a human body in contact with earth, because no low impedance circuit exists for such a current to flow. So that is why the IT system, if you only use one appliance on it, is very, very safe. Because even if it has a fault, you cannot make a fault current flowing basically over the earth, and that's very safe. But however, a first insulation fault can effectively turn an IT system into a TN system, and then a second insulation fault can lead to a dangerous body currents. So that's why if you use a off-grid inverter and install it into your house, into cabin, whatever the case may be, if there is far more than one circuit behind your main panel, you should not use a IT system. You should go for a TN system. Why is an IT system even interesting? You can see here in advantages, you will see continuity of operation. So the IT system in many cases is used in industrial installations where big machines are supplied by isolation transformers, and where it is critical that those machines actually do not stop when there is a fault. So these are really special cases where IT systems have big advantages, and there they are used, but not in home installations. That's why we have to choose one of the 4 earthing systems which do use really a connection towards earth to provide a return path for fault currents. This is the reason why this is actually done. And now, of course, this table here is made for grid installations. So that's why you will see here TNS system. If you look, need earth electrode at site? No. Because, why no? Because this electrode is provided by the transformer or at the transformer, and you are getting the PE wire straight from the transformer to your house. But when it comes to now using an off-grid inverter, then we, as I said before, we are our own utility. So to create a TN system, you have to give this feature to the inverter. The point need earth electrode at site, this refers to a secondary earthing electrode at your property, but you need a primary earthing electrode at your inverter in this case to tap into the earth, so that later on you have a path for fault currents going back to the power source, which is your inverter. So which one would you choose now here if you go for installation? As I said, I would go for a TNS system because we have a very low earth fault loop impedance, because the return current will go through our circuitry back to the inverter and then through our bonding wire directly to the neutral of the inverter. So this is very, of course, the lowest earth fault loop impedance possible. And the secondary part, if a human touches somewhere a hot wire, then it is still the best version there. Yeah, so you see the risk of TN systems is always the broken neutral. From the advantages, it is the safest system what we can choose. When it comes now to the big differences between Northern America and the 230 world, then you will see that in the Northern American system, the central RCDs are actually not used. While in the 230 world, the first device in the main panel is the RCD, and then you have the individual circuits following. That sort of setup is actually giving a leakage protection already from the beginning. Even the whole installation inside the walls, on the way to the appliances, to the outlets, all of this is already leakage protected. So instead of using a central RCD, in America they're using the GFCIs. The GFCIs are actually RCDs which are already just dedicated to the appliance itself. So the most common version is the outlet, the power outlets, which has the RCD circuit, the GFCI built in, so everything what you plug into that outlet will be protected for fault currents. Is that necessarily something bad? No, it's of course not bad, because you don't have protection upstreams of the GFCI, of course, but it still does not really matter, because most accidents will of course happen behind the outlet, of course, inside the appliance. But why does Northern America not use central RCDs like the rest of the world? This, you will see in a moment, has something to do with the lower system voltage. And to explain this a little bit better, we will take a look generally into electrical circuits and how the protective earth system, so the PE system as a raw system without any technical device, is working, and what actually voltage is having to do with that as well. Let's look at the mother of all electric circuits, and that is when we have bad weather, when we have a thunderstorm. Due to rising humidity, air is ionizing. We have negative charged particles, electrons collecting in the air in a cloud, and because the ground is positively charged, when the difference between the charges is big enough, a lightning will discharge, and if it hits our house, we have our lightning arrestor. We are diverting it through our lightning protective installation and diverting it through our earthing rod into the ground. So this is the first ever occurred electric circuit humanity knows of, we need this knowledge actually later on when it's about why does code require an electrode for lightning protection, but why it might not require an electrode for the electrical system. So the next electrical circuit is our grid connection. This is what code is built on. Every grid connection comes with a transformer and a neutral to ground bonded end of the transformer coil, which is earthed there by electrode at the source of power. This here would represent the TNS system, so we are getting then line, neutral and earth supplied to our load center here. And now for us, when it comes to earthing, it is important what happens when the human come into interaction with such a system. So let's assume our human is touching some hot circuit by whatever reason. The other end of the human is touching ground, and fault current will flow from our human back to the electrode of the transformer, and the cycle is closed here. And this fault current can be detected either by RCD, by a GFCI in America, and the circuit can be then tripped. Of course, if there are faults like dead shorts within an appliance from hot to ground, then this will of course also immediately return back to the transformer, and even a overcurrent protection device, fuse breaker or whatever the case may be, will then trip as well. But the important thing to understand is that every time when you have a grid connection, you are married with the earthing at the source of power, which is the transformer. And this will always be there. You cannot get a grid connection without earthing to your property. But now the question is, which we were talking about many times, how does it look like in the off-grid system? I have my solar panels, I have my inverter, and I am getting phase and neutral only. There is no internal bonding usually inside the inverter, other than you choose to do it. Forget it. You can buy an inverter which comes with some features for internal bonding, but by nature we do not have a closed return path to the inverter if we do not install it. So what happens if our human touches again a hot wire? What happens with return current via ground? And this is where we are supposed to choose one of our 5 options, how we can actually then implement the earthing system also for our off-grid installation. So why does some code only require a earth electrode for lightning protection? So that again has to do with the earthing system itself. So if you do not live in a TT system, you see earthing electrode there, of course you need to have one, because it's the only one a low impedance way for earth faults. But most of us users actually are getting their electricity by one of these 2 systems here. Either it's a TNS or a TNCS, and there, especially at the TNS, a earthing electrode is not required at the site, because we have already a very low earth fault loop impedance there. In the TNCS, you see it's optional, and here it's that some countries you need to mandatory install a earthing electrode at your site, but some countries, probably in the United States, will be like that. One commenter, he wrote that earthing electrode only required for lightning protection by my code, and so why should I put a earthing electrode when I put an inverter there, right? So some countries mandatory, some not, but that is only when you talk about grid connection. If you have your own inverter, then you are building your net from the ground up, and if you do not put a earthing electrode anywhere, then you do not have a TN system. So then you're still working with the IT system, and yeah, but even here you see IT system need earthing electrode at the site. Yeah, so because some parts of the IT system, if you have multiple circuits with the IT system, which you can have if every circuit is monitored, then you still need a protective earthing there. So the earthing electrode, when you use your own inverter, is primarily there to create the TN system in the first place, right? Because this gives you the chance that fault currents which are caused by human intervention, by a human who is touching a hot wire and the current is leaking through earth and goes back to your inverter, that this one is then tripping one of our protective devices. Okay, now we have to quickly talk about the PE concept. So PE stands for protective earthing, and this is a raw concept, so not including any technical devices. What is protective earthing actually for, and how does it actually affect this system here when the voltage is lower than in the other case? Let's look at this here. Let's say this is a washing machine, so it is a class 1 appliance. We have line, we have neutral coming in, and we have our protected shell around, which is connected to our PE wire and then of course to ground somewhere. When it comes to protective earthing, it's all about dangerous voltages and dangerous currents for humans. There is a defined safe contact voltage, maximum contact voltage for humans, and in the code here, in the Austrian code, that voltage is defined as 65 volts. It might be different in other countries, in other codes. So 65 volts is the maximum voltage a human can safely touch. And then we have the maximum current. And what the current is actually doing is the current is actually producing the dangerous situation for the human when it comes to the heart, which is the vulnerable part when it comes to electricity and humans. And what we want to avoid is that the heart is starting to fibrillate. So these are the questions here. If we see this, we see actually like a voltage divider here. So all these green symbols here are resistors, and let's now assume we have a fault. We have a line to ground fault here inside our appliance. So we have initially here a resistance for the fault here. So not everything is a 0 ohm state short. There can also be, of course, some insulation materials there or paint, which will then rise the resistance there. And then we are basically on our shell already, and we have two passes the current will then take. So one is then these two resistors, one is standing for the wiring resistance for all our PE wiring until the point of earth, and the other one is the earth rod impedance. And so this path here would represent a certain resistance. And then we have a competing part here from the place when our human touches the shell. We have an initial resistance, which is when he touched here with his hand, so the resistance of his arm until his heart. And then we have a second resistor, more or less, which is from the heart then through the leg until the point of contact to ground. And if you would now look at the voltage drops over each of these resistors and how much current goes which way, then you would here at this point have a maximum voltage of the maximum contact voltage, right, which is 65 volt, and a current which should stay well below the dangerous current for our human here. And of course we have to now follow just Ohm's law, which says that the current is voltage divided by resistance. So there you can see what actually the voltage means in our game here. So if you only have 120 volts input instead of 230 volts, then the voltage here at our heart will be dramatically lower than, of course, with the higher voltage. So if you only have 120 volts at the input and then going over our voltage divider here, you will have a much lower voltage here, contact voltage, than if you start with a higher voltage here. And so you can actually say that the North American system in terms of earthing is the easier and safer option already from the beginning. And the other point about lower voltage is now, of course, that our human, which typically will have similar resistance, you know, a person in America will have probably similar resistances, body resistances like a European or Asian. That means if a human is touching here, a lower leakage current will occur. So if you would actually want to catch a leakage with a central RCD, currents would be lower, so you would actually have to have a more sensitive RCD in Northern America than in the rest of the world. And that's why probably the choice went from a central RCD to GFCI, which is just protecting single appliances. Okay, so what is the conclusion to this video? When it comes to grounding, earthing, this is a very broad topic, especially when you look into the code, because it's also a lot about lightning protection, etc., etc. But in our case, we are really just interested in a very narrow spectrum. We are only interested into creating our TN net if we decide that we want it. At the end of this video, I want to give you another interesting example about this. I was also watching another video of Mike Holt, and this one was about neutral to earth voltage, and he was explaining about this topic, how this is existing inside a grid setup, and that you have rising neutral to earth voltages the further you go away from a substation, right? And then at the end at your property, when you live far away from the substation, due to the long transmission lines, you will end up to build up a certain neutral to earth voltage. And at the end of this video, there was a short Q&A, and somebody asked the question, so how is this in an off-grid system? And he of course said, this does not exist in an off-grid system, which is totally true, right? Because in an off-grid system you don't have long transmission lines, so there is no build up of a neutral to earth voltage. But the person who asked this question asked this probably of a different reason, and everybody who looks my channel knows what this is all about. Because if you install an inverter and you do not ground and bond it, then you will end up with a hot neutral, and that has a different technical reason. It has nothing to do with this what happens in a grid. But of course the answer of the expert was no, this does not exist. So probably the person who asked the question will be now very confused. So why do I see 50 volts, for example, on my neutral if I measure it towards the earth? But somebody said this does not exist. The reason is just asking the wrong question to the expert. He did not know what the question was actually about if it is not explained. But the interesting example is actually last weekend we solved exactly this same thing via the comment section of YouTube. I have two viewers of my channel who have the exactly same inverter. They have an EP-ever inverter, and both of them, they wrote, hey, I have a neutral to earth voltage of 115 volts. Right? This is a 230 volt inverter. So what can I do? Is it safe, really safe to bond this? Because, you know, 115 volts, if I put a wire on that, will the inverter explode maybe? So yeah, so at that time we solved this, and the viewer named XXX, he is now a happy owner of a correctly working off-grid system. So thank you very much for having trust in what I have showed you, and yeah, this is all about this topic, earthing and bonding of an off-grid inverter. Okay, I would say that was it. So again, this is a piece of discussion. Please comment, like the video, subscribe to the channel, and I will see you next time.